Alright, so we're taking a look at the Hardy-Weinberg equilibrium practice problems. And remember, there are two different types of equations we're going to take a look at. The allele frequency equation, which is P plus Q is equal to 1, and the genotype frequency equation, where we're taking a look at P squared plus 2PQ plus Q squared equals 1. So you have to take a look at what are you being asked. Are you asked about alleles or genotypes? So here we have in the gene pool, we have a dominant allele is being represented with 0.19, and then the recessive is 0.81. Calculate the percentage of heterozygous individuals. So for heterozygous, we're going to take a look at 2PQ. So 2PQ is going to go ahead and be 2 times 0.19 times 0.81, and okay, the answer should be 0.31 or 31%. Okay, for homozygous recessive, we're going to look at this equation, and Q squared is going to represent homozygous recessive genotype. Okay, so in this case, if Q is 0.81, we're just going to square it, and it should be in terms of 0.66, or in other words, 66%. Okay. Here we have the frequency of homozygous recessive is going to be 0.09, so that represents homozygous recessive is going to represent Q squared. That's what's given, 0.09. But it says, what's the percentage of individuals that have the homozygous dominant allele? Well, if that's the case, we're going to have to find out what Q is so that we can find the dominant allele, which is P. And when we do that, when we isolate Q by itself, we need to go ahead and square it, which should be 0.3. So then we can use that information to take a look at the allele frequency. And so if Q is 0.3, what is P? P should be 0.7 and or 70%. Okay. Since we're taking a look at homozygous dominant, okay, homozygous dominant would be represented by P squared, so we're just going to go ahead and square it, so it should be 0.49 or 49%. Okay. Alright, so the next one we have 38% is going to be homozygous recessive. Okay, but it's out of a population of 14,500. So calculate the homozygous dominant individuals and also the heterozygous individuals. So if we know that, okay, we're taking a look at 38%. What's given is homozygous recessive, so that would be Q squared is 38% or 0.38. But if I want to go ahead and isolate it, square root it, so then we should get 0.62, right, or 62%. So knowing that Q is equal to 0.62, we have to isolate it so that P is equal to 0.38, and then we can use that to calculate P squared, which is homozygous dominant, and also heterozygous, which is 2PQ. So 0.38 squared, and 2 times P is 0.38 times Q, which is 0.62. So this would be 0.47 or, 0.47 this is 0.47. This one is the first one is 0.14. But it's asking to calculate the number of individuals, so this would be 14% or 47%, but it's asking what's the, calculate the number of individuals for the two genotypes. So since it is going to be out of 14,500, I'm just going to write it here. You got to multiply it to see what is the value of that population. So here it would be, I believe it's 2030, and here it would be 6,815. Here we have tasting the trait is dominant and not tasting it. So out of 400 students, 64 were going to be non-tasters or otherwise homozygous recessive. So we want to see how much heterozygous, what's the percentage of heterozygous students there were. Well, if this is homozygous recessive, this value out of 400 is going to represent Q2, or Q squared, I mean. So it's 64 out of 400, and that would lead to 0.16 or 16%. But we're trying to go ahead and find the value of 2pq, and in order to find q by itself, let's go ahead and square root it. And if that's the case, we're going to go ahead and see it as 0.4. Okay. So knowing that, since I have Q, I can isolate it to have P by itself, and P should be 0.60. Now if I have those, that would represent 0.6 times 0.4, which should come out to 0.48 or 48%. Our next one is, we have our kernels here. Okay, out of 100%, 9 of them are homozygous recessive, so that's going to represent Q squared. Okay, so Q squared is going to be, what is it, 9 out of 100? 9 out of 100, okay, and we're asking for the frequencies of yellow and white alleles. So if that's the case, and we isolate, so this is going to be, what, 0.09, but if we isolate Q by itself, we're going to get 0.30. Okay, and if we know what Q is, we can go ahead and figure out what P is, which should be P is equal to 0.7. Alright. Alright, let's take a look at the back. We have 2 Siamese and 3 Persian cats. They were shipwrecked. Okay, all 5 cats have normal ears, but one of them has the recessive allele, and their genotype is that. Heterozygous. So if there are 5 cats and all of them are homozygous dominant, okay, and one is heterozygous, okay, let's say in a gene pool, these 4 cats,
Pinocchio, please dial 2252.
These 4 cats, they'll have in their gene pool, they'll have these dominant alleles. So it would be 1, 2, 3, 4, 5, 6, 7, 8. Okay? But there's this one cat that is heterozygous. So that's what it would be in the gene pool. So if that's the case, okay, what would represent on the capital F, there would be 9 of these dominant alleles out of the 10. Okay, so that would be 0.9, or in other words, this would represent P. Okay, P. What would represent Q, which is a lowercase, is the 1 out of 10, or in other words, 0.1. Okay. Now it says, assume, how many cats would you expect to have folded ears when the island population reaches 20,000? So folded ears is going to have that recessive allele. So we're going to go ahead and we know what Q is. We're going to square it. So 0.10, okay? And then multiply it by 20,000, because there's going to be 20,000 cats. And you should have 200 cats. Okay? Alright, last one. This is going to combine chi-squared and the Hardy-Weinberg. So in this case, we have hair straightness and curliness. We have it being shown as incomplete dominance. Okay, so for straight hair, it's homozygous. Okay, so it's curly, but then wavy is heterozygous. Now, it says that there, out of 100 individuals, 245 are going to have straight hair. Now, here's the thing. It's not just 245 that will have this phenotype, but when we break it down and take a look at the alleles, okay, for every one person, they're going to have two different S alleles. So for every phenotype that's here, the genotype is homozygous S, okay, each person has two of those S alleles. That means how many total S alleles are there? Well, since each person gets two, it should be 245 times 2, which comes out to 490. And they don't have any C alleles. Same thing for here. If there are, how many people? 393 people that have curly hair. Yes, well, 393 people have curly hair. For a genotype, one person is going to have two of these C alleles. So it's 393 times 2, which is 786, and they're not having any S alleles. Now the last one is for wavy hair. This is how many people that have it, but for each person that has it, they're going to have one of their alleles that's going to represent the S, and then the other is going to, of their genotype, is going to represent the C. So that's why it's like that, okay? So when I go ahead and add it, and it's going to be out of the 2,000, so it would be, if I add how many S alleles are there, there's going to be 852, but out of 2,000. Here it's going to be 1,148 out of 2,000. So this should be 0.43, and this should be 0.57. Okay, but we're not done yet. We're going to take a look at the observed versus the expected. Well, the observed for straight hair, we know it's 245 people. Here it's 362 people that have it, and 393. But what do we get as the expected? Well, in this case, for the straight hair, 0.43, what's expected out of 1,000, because remember this is P squared, right? So it's going to be 0.43 squared times 1,000 people, and that should be 100. This is what we should expect. For 2PQ, okay, it'd be 2 times 0.43 times 0.57, okay, divided by, multiplying by, all of that is multiplied by 1,000, okay, times 1,000, and so this is the times. That would be what, 490. That's what we're expecting. And then for curly haired, we're taking a look at Q squared. So Q is 0.57 squared times 1,000, which is going to be 325. Now when we go ahead and take our observed, and I'm just going to go ahead and do this for the first one. Observed minus the expected divided by the expected, square it, divided by the expected. So here we should have like 60 squared divided by the expected is 185, but we're going to add this to this one. It should be negative 128 squared out of 490, and this one would be 68 squared divided by 325. Okay, what we should have when we add this, it should turn out to be what, like 67.1. That is our chi-squared. So here, the chi-square value, is it greater or less than, oh well, first for 2, it's out of 2 degrees of freedom because there's 3 different categories, and for the degrees of freedom it is the number of categories minus 1, so there's 2 degrees. So when we look at this chi-squared, we're taking a look at this value right here. Okay, that value right here, 5.99, and we compare that to 67.1, and the chi-square value is greater. So if it is greater, the null hypothesis can be rejected. The data does not fit. All right. So make sure you fix your answers, and if you